today I'd like to discuss with you again SambaFlow and just how to bring your models over onto your DataScale. And I'll touch on Model Zoo, Model Box, and take it from there. So just as a brief overview, SambaFlow is our Python SDK, and it's your interface with our platform for how to compile and run your models on the DataScale system. With this, you can train your models, you can fine-tune them, and you can enable them for inference, what have you. And we have three main ways of distributing these models. One is bare metal. That's you coming in with your model, applying some conversion that work on our platform, and then deploying on the DataScale. We also provide Model Zoo. That's a very new feature. Jennifer and Somi can talk more about that. But it's really built for helping you to integrate and onboard open source models, for example, Llama 2. And then there's Model Box, which is sort of a containerized means of deploying a precompiled model. So bare metal, good for custom models. A Model Zoo is good for adapting existing models in open source. And Model Box is ideal for executing models that have already been built. This is sort of the bare metal workflow at ALCF. On the left-hand side is where you begin, and that's your compilation phase. And in point of fact, compilation only requires a host. You don't actually need RDUs to compile a model. So what happens is that the host compiles your model, generates that PEF, and then that PEF can then be deployed onto other ALCF DataScale nodes via a distributed training launcher. So in ALCF's case, that's Slurm. So Slurm would deploy your application in the PEF onto the nodes it controls as part of the cluster to run your job. And it will then, of course, give you the results of your run. And you can take those results and you can analyze them, use them to make checkpoints, and use that feedback to, of course, rerun your model, right? So it becomes sort of a virtuous cycle. Compile, run, train, analyze results, feedback, and continuous loop. With Model Box, that sort of changes. You still have the execution phase. The container gets deployed onto the node via the launcher, Slurm. Results are gathered and feedback is used. The compilation, though, happens at SambaNova. So we pre-compile the model for you, and then we package it into a container along with its dependencies. And then you would use that to deploy and run your job. So it sort of makes things a bit easier for you, is the idea. And some details about the Model Box. So a Model Box is a container image, and it encapsulates sort of the model, the PEF, as well as the APIs and compiler versions that were used to compile that model. Really, you can think of it as sort of like a microservice, and it's meant to compile and run a single model on RDU. It provides standard interfaces. So the model communicates with ALCF nodes via standard interfaces, Slurm. And the actual runtime on the bare metal, on the host, is what actually executes the model from the container. And as I mentioned a ways back, the containers are all OCI compliant. In the case of AML, they're singularity containers. And the box on the right of the slide gives you a sort of snapshot of what the container looks like. You have the SambaFlow compiler in it. You have the model application, the actual code. You have the configs that are associated with it. These are usually written in YAML. There's a gPracy server that's optional. That's usually used for inference, communication, things like that. And then, of course, within the model app, there's also the model PEF. So there's the code and the PEF. It's all in the container. Now, to go a little bit further beyond that, there's the Model Zoo. And what the Zoo is going to be is a library of RDU compatible model source code, along with any sort of like runner scripts. So scripts for compilation, scripts for running, scripts for inference, what have you. Those are also kept with the model. And the compiler, those dependencies, those are all made available through a container image, for example, Singularity. And the zoo is meant to be compatible with open source checkpoints. So, for example, Hugging Face and Llama 2. Now, we won't give you the checkpoints. You can download them from Hugging Face. But that's how you would use the zoo. And the idea is really for you to use the model zoo to more easily onboard and adapt an open source model of interest to the SambaNova platform. So you start with your base, Hugging Face, pure PyTorch. You check if there's an existing model already, like do we already have it internally in the zoo? If we do, then you just download that. If we don't, then we would adapt that SambaNova model or the Hugging Face model to be compatible. You can then use that to run your experiments, check accuracy, check performance, whatever metrics are of interest to you. And you can then take that model after you've trained it, fine-tuned it, and then deploy it, all on SambaNova, on your DataScale systems. And this is sort of another overview of bare metal versus zoo versus box. So on the far left, we have bare metal. And this is for the ML engineers, people that usually work with the bare metal, right? It's for the end-to-end development of a custom model. So on bare metal, you can execute, you can compile, you can modify, and of course you can have your model definition all there. Examples of this at A&L would include something like Cosmic Tagger, or AutoPhase NN. These are custom models that are very well fit for the bare metal DataScale system. In the middle, you have the zoo. So you can modify and develop existing SambaNova implementation, right? So you can execute, you can compile, you can modify, but you're basing it off of pre-existing work. So again, this would be like your Llama 2s, your Mistrals, what have you, in that they exist and you want to make them work for you, your use case on SambaNova. This is what the zoo helps you accomplish. And then the model box, this is for execution, for deployment. So the source code is already optimized for SambaNova. You already have the test, it's already compiled for either an RDU or multiple parallel operations. And you're just going to use that to train your model or run inference or both. So there's a spectrum here, right? You can go from raw custom code all the way to something that is deployable out of the box. All depending on your use case and what you want to do. Okay, and that's the meat and potatoes. I've talked to you about model zoo, I've talked to you about compilation, talked about runtime. But now it's a matter of, okay, Craig, how do I actually take my model and put it onto SambaNova? What does that involve? Unfortunately, it's fairly straightforward. At the top, keep your model as pure torch. Just take your torch model and bring it on over. The first thing you would do is that we have a function called samba.fromTorchModel_. And what that does is it will take your torch model, that compute graph, convert it into parameters that are consumable on the RDU. We call those Samba tensors. And all that does for you automatically is take your torch model and make it ready for Samba. There's no need for you to do anything else to that model to make it work. From there, once the model is converted, you can compile it. That's just a samba.session.compile, one command. Now there can be adaptations, right? We don't cover the entire gamut of torch functionality, right? PyTorch is huge. SambaFlow, we don't cover all of it with it yet, but we do cover a subset that covers 85% or more of the use cases that you would use Torch for. And then once you have it compiled, you run it. That's via samba.session.run. And there's another function called utils.tracegraph. And that is we'll discuss what that does in a little bit. So some best practices with SambaFlow. You want to make sure your input is well defined. So that means not just the input tensors and the output tensors, but also any internal tensors. And what I mean by well defined is that I mean that the tensors shouldn't have operations on them that aren't torch operations. So don't take your torch tensor and modify it in place via say Python operations or NumPy operations. Only call torch ops, so add, multiply, what have you. The compiler needs to be able to see all of the symbols. It needs to see the symbols that are input, so it's coming in. It needs to see how the symbols change internally within the graph, and needs to see the output shapes of those symbols. It needs to see the whole flow to understand how to best map it onto the RDU. The key thing here about the RDU is that we are a data flow engine. We do pipelining. So our goal is to take your model, the graph of that model, and map it onto RDU such that it forms a single continuous flowing pipeline. That's why we need to see all those symbols, so that we can have one contiguous graph. And that's the next point. Try to keep all your operations in one single continuous graph. That's because, again, we want to be able to map the entire thing onto an RDU or several RDUs. And if you split your model up into different sections, that would potentially necessitate compiling each of those chunks individually. And therefore, they won't be optimized appropriately to connect. So to keep it all as one continuous flow. Avoid control flow. So if your forward section in your model contains conditionals, if else, SambaFlow doesn't yet interpret those. The compiler doesn't understand those. At best, we would just compile for the true path. Whatever evaluates the true, we will do. If there's any checks to see if there's things coming in that are false, those will not be captured by the compiler. So within your model, when you bring it over to SambaFlow, make sure there's no control flow within it. Now, much as you can with CPU and GPU, you can synchronize between RDU and CPU. You can transfer tensors in memory between the two. But of course, just like with GPU and CPU, that comes with a high I/O overhead, right? It takes time and to transfer that data back and forth. So as much as possible, keep everything on the RDU. But, there's a large memory pool there. You can fit a lot of the model in that space. So you shouldn't have to go to the CPU too many times. Then of course, just keep it pure torch. Only convert when needed. The fact is that SambaFlow and the compiler are very smart. When they see a torch operator, they'll automatically replace it with the equivalent SambaFlow operator. And I'll go into that in a little bit. So these are sort of the best practices. And if you stay within these lines, it's pretty simple to bring over a torch model onto our platform. So I mentioned this earlier, SambaTensor. What is it? Well, at the basic level, it's just a wrapper around a torch tensor with some special SN sauce sprinkled onto it. So for the purpose of our compiler, each SambaTensor has a unique name. Now you can specify this. So when you create a SambaTensor, there's a name field that you can add in, or you can let the compiler do it for you. But that name for that tensor at that time will be unique. That way the compiler can track the flow of that tensor throughout the entire graph. There's an optional batch dimension you can specify. If you don't specify it, then one won't be used. But of course, you can specify which one is the batch, and batching can be used for optimization, right? It can help you manage memory, what have you, compute resources. Beyond that, the SambaTensor behaves exactly like a torch tensor. You can add them, multiply them, reshape them. Anything you do with the torch tensor, you can do with the SambaTensor. And on the right, you see a few of the built-in functions that we have with our SambaTensors. So the .data method will give you back just the pure torch tensor of the SambaTensor. .batchdim will give you back the batch dimension. dtype gives you back, which you might expect, the torch data type. The two special ones, SNName, SNGrad, those give you back the specific information about the SambaNova tensor, the Samba tensor. So SNName gives you back the name of the tensor. And SNGrad actually gives you back the gradients of the tensor on the RDU. So if you want to see the gradients of that tensor, you can call SNGrad on it, and they'll be dumped out of the RDU for you. And then the last two, .cpu and .rdu, these are similar to what you have in Torch for transferring between RDU and between GPU and CPU. .cpu will take the tensor, dump it out to CPU, and .rdu will dump it out of CPU onto RDU. You can do this with any tensor you'd like. You use entire models. So if you want to transfer a model from RDU to CPU, you would call the .toCPU method, and vice versa, it'd be the toRDU method. And of course, you don't have to do these things. Don't do them. These are expensive operations. They require I/O between the RDU memory and the host memory. And that, of course, slows down your model. So I've mentioned having your graph stay as a continuous flow on the RDU. And I've mentioned having to track and trace your tensors through the graph, right? How they change. We call that tracing in our parlance. And what tracing is just literally walking through the graph with tensors to see how they change. So we call those tensors dummy tensors because they don't have to contain real data. What they have to be is that those dummy tensors have to be the same shape and the same types as your input tensors. What the compiler cares about is not the data within the tensor. It cares about the size and shape of that tensor. So of course, as you're mapping the graph onto RDU, you're mapping into silicon, right? You're actually changing transistors to look like your model. So you need to know the type of the tensor, because that of course affects the size of the tensor in memory. So it will affect the size of the tensor on RDU. And since operations will change the shape and size of the tensor, that's why we need it to be the same size and shape as your input tensors. And what this lets the compiler do is actually track how the model transforms your tensors into output. And that lets it map, optimally, your graph, your model graph onto the RDU. This is automatic. So when you call compile, it does this tracing for you during the compilation step. You would do it manually with the trace graph function, and you do that during a run. So when you're training your model, before you say train the model, you would say trace graph, and that will trace the path onto the RDU with the dummy tensors. So it prepares the RDU to be ready for the training run. And this is all beneficial to the RDU. For example, because by default, that O3 I mentioned, that O3 compilation flag, that's our default. So we try to do the entire model at once. So that's part of why this tracing is so important, is that it gives us a picture of the full graph so we can optimize it appropriately and map it on efficiently. And you can see the little graphic of that on the right. Input tensors A and B, they get added. They have an output tensor C that gets fed to a linear. The linear has weights, and then all combined, they produce the output D. So A and B are dummy tensors. They don't contain real data, just the shape and data type. And then they get transformed by torch ops. So the A and B are well-defined. B, the output, because it came from a torch operation or Samba operation, it's also well-defined. Same with the linear. So this is how we trace and graph and map the model. So the tracing is based off of the model definition. Specifically, it's based off of the model's forward path. So to reiterate, no control flow in the forward, right? No ifs or else's. But it's the forward path that we use to actually define the trace and the model on RDU. There's no need to define your backward path, much like PyTorch. We do that automatically. The major difference, though, is that we actually, not only do we map the forward path onto RDU, we actually map the optimizer and the backward path onto RDU at the same time. So it's one single flow. And again, compile, we call it compile method. And for training, you would call trace graph. And those will both trace the model onto RDU. So another neat feature of SambaFlow is that we support functional overrides. So if you've been using Torch for a long time, if you've used NumPy at all, then you might be aware that if you call a Torch function with NumPy arrays, Torch will automatically override and call the equivalent NumPy for you, the NumPy function, or vice versa. We do the same thing. So when you feed a Torch function a Samba tensor, we'll see that, Samba will see that, and automatically call the equivalent Samba function. You can see here on the right, we have Samba tensors A and B. We call Torch add on A and B. Our SambaFlow, and thus our compiler, will notice that and replace that Torch add with a Samba add. And from that, we'll do our inferences, we'll check our types, our shapes, we'll produce a Samba tensor output, C, and then that will be connected into the graph as a A and B node with an add op that it produces a C output. And that's all transparent. And this is why I said all you have to do really is run Torch model, convert your model, and not much else, because we handle the actual most of the conversion for you. We see your Torch ops and replace them transparently with Samba ops during the compilation. So you don't have to go through and actually manually replace all your Torch ops with Samba ops. And we have a full SambaFlow API documentation. I'll show you that a bit later, but all the functions that we support are in there. And here's an example of a model definition. So this is a feed-forward log-reg network with residuals. And it's fairly standard, right? You have your init. It makes use of gems as linears. It has layer norms. It uses a sigmoid as a activation function. And this is a bit unique, but it has a loss function in it. And then, of course, we have our forward. And our forward, of course, is what we use to manipulate our inputs, right? What we actually use to train the model. So modules, they use parameters, so linear, layer norm, things like that. Those should be defined before your forward, right? Put those into your init. And then your forward, that should, the caveat there is that the return type should be kept simple. So it should either return a tensor or a tuple list of tensors, right? So don't try returning complex objects. Just return pure tensors and you'll be good. And something I want to call out here. So you'll notice that in the forward, we are actually calculating our loss, right? You'll see self-block criterion, out, and targets. Something that SambaNova lets you do is actually run the loss function as part of the forward path. So when you map it, it will map the forward onto the RDU, so all your layers. If you have a loss and optimizer, it will map those two, and then it will map the backward path. And the compiler will ensure that all the right nodes are connected such that the loss is fed to the optimizer, and those details are fed to the backward automatically. So, so long as it's a loss function that we support, because SambaFlow doesn't support every loss function that Torch does yet. But if it does, then that loss function can be placed onto RDU, and you can do your entire path in one sweep, instead of having to pause and do loss and then resume functionality like you would on a GPU. So it can keep things more efficient and more optimized. And then here's an example of the app code. So the application on RDU, the process is two parts. First, there's the compile, then there's the actual training loop, so the actual run. So to start with, as I mentioned, we use dummy tensors to do that tracing. So at the top here, you see image and label. Those are random numbers. In Samba, we have support for random numbers, so we support randin and randint. And we use those to generate tensors that are the same size, shape, and type as the model expects. So in this case, it's expecting to run that resFFN logreg. So it's in the right shape for that. Then we have our model. The model's defined as you normally would with Torch. And then you call from Torch model on it. And that just in place, so it's an in place call. So from Torch model underscore, that follows the PyTorch convention of in place operations having a trailing underscore. So the model gets replaced in memory with Samba tensors. And then you can call it as you normally would. We define an optimizer. So out of the box, SambaFlow supports SGD and AddNW. We define your optimizer there. And then, of course, we check. Are you trying to run or are you trying to compile? Right. So at the command line, when you call the model, you would call it with a run or compile. If you call it with a run, then we will do a trace graph using the model and the path that we generated. And then we'll call our train loop. So in this case, we've encapsulated our loop in the function train. If you're not running, so say you're just compiling, well, then we call session.compile. And that's where we pass in the model, we pass in the inputs, we pass in the optimizer. The name isn't required, it's optional. And init output grads is also optional. So it's really just a check for if you're doing inference or not. And that's really it. All you need to get the model compiled and to start training process. When you run, there are different ways to run the model. So you can run it fully. So all the sections, forward, backward, optimizer, you can run all those, and that's the default. And you see the example up here running all the sections. So call some decision.run, you can gather the outputs. And the outputs will be the outputs from your forward, right? So run outputs your forward results. From that, you can do what you will with the results. For example, we call back to CPU on session and send the model back to CPU to do any operation that you might want. That could be, for example, you want to say maybe deploy to another system, on CPU or another node, or you want to do calculations or visualization. So you say you want to visualize the developable model, you should, output the tensors back to CPU for that. Or you can dig into the model and actually pull out weights and gradients for individual operations and layers. So here we're pulling out the weights from the linear layer, the first one to be particular. Or you can actually just run specific sections. So for example, in the second example, in this second box, we're calling section types equals forward. So what this does is actually just puts the forward section of your model onto RDU. And you do this for inference. So if you're only running inference, you don't need the rest of it, right? So you can just apply the forward. What you run and what you decide to, actually put on RDU is up to you, and depends on the use case, as always. And here are some examples of compile and run commands. Some standard arguments that you would use for these things are, for example, inference, if you want to compile a model for inference, batch size, micro batch size, PEF, what you want to call the PEF file is what you specify with that. And these are just some examples. We provide a facility for you to define any argument you want to be brought into SambaFlow. So if you have a custom model and you have, say, custom arguments or hyperparameters, you can define those and bring them into SambaFlow without issue. If you look at the example compile command, you'll see this function called parse app args. And that's a built-in function that we have, part of SambaFlow utils. And it lets you parse any custom arguments you have from the command line. So whatever you want to bring into SambaFlow, you can. And of course, you specify micro batch size, which you're compiling for inference, true or false, what have you. And then, of course, the run command is based off of your compile command. So you compile, say, app.pef. When you run it with app.pef, right? You just pass it the pef file. And of course, you make sure that the micro batch size, the batch size, match what you compiled with. You don't want to try to run a model with different arguments from compilation. Those are connected. in SambaFlow. And sort of as a helper, so we have Samba tensors, which wrap around our Torch tensors. Well, we also have a Samba loader, which wraps around Torch data loaders. This provides a very convenient means of feeding your data into an RDU. So the RDU, of course, works with Samba tensors, so it expects those. So typically, if you're, say, sending input to the model for training, each tensor you get from the data loader, you have to convert to a Samba tensor. Well, Samba loader does that for you automatically. You just wrap it around your data loader, and as your data loader runs, it passes tensors out. Samba loader captures those tensors and converts them automatically for you. Another added benefit is that Samba loader is, of course, RDU aware. It knows about the RDU, so it can actually help parallelize load operations with graph operations. So Samba loader can better utilize your RDUs when loading large amounts of data. And as I mentioned, instead of having to manually convert your Samba tensors to feed as input your model on RDU, the Samba loader automatically outputs an iterator over Samba tensors. So Samba loader will automatically give you those. So there's no need for you to do the extra hassle or extra step of a conversion. And below is an example of what that looks like. So you import your data loader, you import the Samba loader, you define your data loader, and then your Samba loader just literally wraps around that data loader. One caveat is that, again, Samba tensors need names. So the Samba loader lets you pass in a list of names to get to the tensors coming out of the data loader. So for example, here, we're just calling them sample and label. Then of course you call your training loop, your run, off of the Samba loader. So for X and Y in Samba loader, run, and you pass in the necessary inputs. So that makes it a bit easier to load your data. Okay. Now that's sort of the high level. All the information I've shared with you, not just this session, but last session, are in the developer docs. We have examples to try, SambaNova tutorials, and of course the support team is available to you. Now I want to show you I want to show you a little bit in our documentation and a little bit in our tutorials, but I want to check if there are any questions or anything before I show those things.
I think most of the questions were answered by Darshan. But if folks if you still have something to add on to Craig, that would be great. Or if anyone else have any questions, please use the chat window to post your questions.
Okay. Well, I see Darshan and Soumya have been very active and they know their stuff, so I'll let them handle that. I'm going to move on and do a quick overview of our documentation and our code example, places that you can go look at.
Sure.
So our docs, docs with SambaNova AI. These are open to the public. You can navigate to that address and you can see them. Here are the developer docs. So literally everything that I've covered today, the compiler, the runtime, conversion, examples, they're all right here for you. So the optimization modes for compiler I talked about, 01, 03, here they are. Here's the full details, even more detail than what I gave during the discussion. Here's a deep dive into the compiler itself, sort of what it looks like, what it does. If you need examples of how to convert a model, right? So we have a basic hello SambaFlow, sort of like hello world. We have additional tutorials. We have this model conversion 101. This goes from a raw Torch model, an actual convolutional model, really, and we'll walk you through step by step from raw model and raw data into an actual SambaFlow model that can be deployed and inferred from. The full process. And it goes step by step how to approach the problem. And of course, we have an overview. So this learning map, this guides you. You can go from left to right, and it will walk you through the entire SambaFlow stack and how to use it. Very, very useful. And we'd love for more people to use it, honestly. There's a little feedback button up here. So if you have questions or see things that aren't very clear, you can give us that feedback. And I know for a fact that the documentation team would love your feedback. So please read the docs, talk to us. We'd love to hear from you. And of course, we have additional guides, for example, data parallelism, tensor parallel, how to use mixed precision, like messages and logs, those references there, hyperparameters, torch operator support, we have that. Tips and tricks, little things that could help you. And of course, we have the API reference. So SambaFlow, this isn't all of the API yet. We're adding more to it. But for example, you want to see Samba tensors that I just discussed? Here's that, and here's everything you can do with that Samba tensor. Every method, every function, all the arguments. Very, very deep. I think this particular API entry is like 25 pages long. All the detail you could ever want. And of course, we have functional operators. So for example, absolute, add. These are all the operations that I mentioned that we can understand directly from Torch. If you call Torch add, we replace it with a Samba add, right? And this is the full list of all of the functions that we do that for. And this is ever growing. So if there's a function here that you don't see, but that you use, reach out to me, reach out to Jimmy, reach out to Jennifer, open up a Salesforce case, support, and something that we can get on to enhance. Okay. And then I did mention extra tutorials, right? So from over here, also in how-to guides. So this is a public Git repo, github.com/SambaNova/tutorials. And here we have 3 examples. We have Lynette, a Hello World. We actually have a generative NLP example that you can go through. This code is all available to you. You can download it and you can run it on the SambaNova system. It comes with full readmes, and these are bare bones. They go from the raw models and the data, and they tell you how to prepare your environment, how to check your environment, how to get the code, how to get the data sets, how to compile, how to train, everything. He's walking through all of it. Oh, yeah, thank you, Renata. If you look in the chat, Renata from our document team, she just shared the link to this. So, all the details you could really want to dive into are available. And this is a sort of like final little teaser. We have the AI starter kits. So these are more advanced examples of what's in the tutorials, and they're LLM based, and they can integrate with for example, our Sambaverse. And they provide use cases for things like Q&A, knowledge retrieval, fine-tuning for SQL, fine-tuning embeddings, prompt engineering. These actually go from the ground up how to build these things and use them and use SambaNova models to deliver them. And these are very, very detailed. And again, feedback is welcome. So if you use them, let us know how they go, and we'll take that to improve. And again, this is all public, so you can, clone this repo, you could fork it, what have you. And that's all I have for today.